Hello, everyone. Good morning. Today, Rob and I will talk about network reliability in Meta's AI training clusters. First thing I'm going to do is going to give you some context about some different network topologies that we have and how do they fit within the AI training ecosystem. So if we look at this topology, we call this topology the front-end fabric. This is a multi-stage spine and leaf topology that fundamentally we use for a wide array of use cases, including AI training. This is our workhorse topology. And in the context of AI training, this essentially provides a couple of functions. First, it's used to do data ingestion. It gives us the ability to initialize and manage the communication libraries, and we use it to optimize the control plane. This network is highly scalable, highly performant, overall highly redundant as well. And while that network is great, we need to have a dedicated network for the use case of multi-GPU communications. And we do this because essentially we know that this type of use case requires high bandwidth, low latency, and is extremely sensitive to any sort of disruption, such as packet loss. Having this dedicated network gives us many benefits. It simplifies network management. It simplifies network tuning. But more importantly, because it's geared to a single use case, it also gives us the ability to use specific platforms, specific configuration, and specific tuning to HPC. When we combine both of them, we essentially have a solution that caters to a wide set of needs. The front end provides this general use case, highly scalable, highly redundant solution, and the back end essentially provides this capacity to have very specialized topologies and to experiment with a single use case in mind. Hopefully, this provides a bit of color of what are some of the networks that we're going to talk about and the challenges that we have for reliability in them. But let's expand on this a little bit. So this topology is the backend topology, just the wider version of it. And if we go from the bottom up, we have the host. Each host has usually 8 accelerators. We have 2 hosts connected to each leaf. The leaf we call RTSW, or rack training switch. This leaf is connected to each other via spines that we call CTSW, or cluster training switch. And ultimately, in this particular topology, we have 18 on them. This is undersubscribed. This provides an operational buffer. It provides the ability to do maintenance. And if there's any failure here, we obviously want this to be addressed quite quickly. The scale is that we have around 252 RTSWs. This gives us around 4,000 GPUs in essentially what we call an AI zone or an AI cluster. So let's introduce a failure into this topology. If CTSW9 has some sort of issue, we want a solution to be able to quickly identify that this is happening. We want to be able to do triage, essentially having the ability to understand which network element has the issue and which network element essentially is just seeing the after effects of this, and execute a mitigation, whether that mitigation is automatic or that mitigation is essentially going to send this for a physical repair. Let's talk about what are the challenges in doing this at scale. There's many challenges. We basically have these 3 groups in mind. The first one is observability. The performance and the reliability of this training cluster hinges on our ability to consume a vast set of data, sometimes from sources that are really don't go well together, and to be able to provide answers to questions such as, do we see any obvious disruption? Do we see anything that indicates that we are dropping packets on the floor? Is routing healthy? Is the hardware itself healthy? Do we see any ASIC level errors? And in some cases, in a more predictive way, do we even see slow degradation in resource utilization? This can be things like CPU, memory, or this can be things such as temperature as well. And this brings us to the second theme, which is triage. With consuming all of this gives us a lot of different pieces of data, but we need something that is able to put this all together in a way that is automatic, in a way that is highly accurate, and in a way that is highly performant. If any of those doesn't quite hit the bar, we usually need to involve humans, which is something that we want to not do because this introduces latency and introduces variability into this process. Ultimately, we need to be able to identify which is the network element that is having the problem in order to take an action on it, which is usually going to be to put it out of service, to remove traffic from it. Because if you remember the topology we saw before, a single one of these devices will affect, in that case of that topology, 1/18 of all traffic flows across all of those GPUs. And this brings us to the last challenge, which is capacity impact. We have that operational buffer, but especially in the case of AI, capacity is directly tied to performance. So as soon as we take one of these actions and we take one of these devices off the network, we are essentially less redundant. We have more risk. And we have to be very mindful of avoiding what we call excessive draining or over drains, because if we go beyond the failure envelope for the network, the entire cluster is going to be degraded, and this is obviously not what we want. So we want to make sure that we have protections in place, that our repair actions, our mitigation are sane, and that we can bring that capacity back online as quickly as possible. I also want to make the note that this is not unique to the backend network. Both networks have these challenges, but the backend network does have a higher reliability bar, and this has been the forcing function for our teams to rethink and reimagine how do we do some of these operations that historically we were doing for quite a while. And with that, I'm going to hand off to Rob to talk about what are some of the strategies that we have implemented to address these challenges.
Thanks, Jose. With these challenges in mind, let's talk about how we've evolved network tooling and processes to support large-scale training jobs here at Meta. Our starting point was to ask the following question: can we predict and mitigate failures before they impact jobs? So let's explore. So to evolve our approach to network management, we had focus on 3 strategic themes. The first is integrated monitoring. We combine both passive and active monitoring techniques with an overarching SLI framework to give us increased visibility to observability events and SLI impacts. The second is our enhanced triage. We refined our triage process to be both topology aware and event aware, so we can do correlations across both topology and event details. And in addition, we added an on-box agent to allow for escalated manual triage. And then finally, we're talking about our rapid repair function, which is surrounding implementation of strict SLOs and focus on that mean time to repair, returning devices to service. This rapid response capability is a key to maintaining resilience and efficiency and ensuring the network is highly available. So let's talk about integrated monitoring and what that means at Meta. So passive monitoring is what most people would consider to be traditional monitoring. It's about detecting, triaging, and alarming on-box events, right? And these could be SNMP, vendor-specific counters, log patterns, et cetera, et cetera. And the issue here is that we run a heterogeneous network, so the monitoring space is very, very fragmented. To that end, we implemented a custom on-box agent that unifies this detection space and allows us to do real-time aggregation and trending on collections. The other thing that this on-box agent allows us to do is it allows us to do combinatorial lookups and have look-back windows, right? So this helps us reduce the noise coming from our detections and essentially gives us a much more finer signal based on the events that are coming in. The second part of integrated monitoring is active monitoring. And for this, we need to establish a clear and constant baseline of packet loss across our network, packet loss and latency. We do this via distributed measurement agents across both our TCP and RDMA networks. And these allow us to do loss and latency aggregation across network scopes like rack, pod, and AI zone. We look at this as a wide lens view of network health because it gives us a view into problems that potentially you don't see on a per device basis. So at a high level, this is what our strategy looks like. Passive monitoring, we're detecting problems on the on-box agent, and we're forwarding it onto triage. On the active monitoring front, we use NetNORAD, which is our foundational loss and latency measurement platform. This looks at each minute of delivery in a particular scope of the network, and it looks at our established reliability thresholds. If it's below our established reliability thresholds, it marks it as a bad minute. We take contiguous chunks of bad minutes, and we send them to the NetSLI framework, and this creates an event. This event then gets decorated with things like passive monitoring data or real-time collections. And this allows us to attribute a root cause to the loss. And then that also flows downstream to our triage process. Since these both flow downstream to our triage process, let's take a look at what that looks like. So even with the noise reduction in passive loss in the passive monitoring and with the loss thresholds in active monitoring, we still end up with thousands of uncorrelated distinct events across multiple layers of our network. You can look at this sample right here. We have a host with reduced throughput. We have an SLI impact on the DC level. We have BGP port down and peer down on the spine level. Looking at this sample set right here, it would be very hard for anyone in this room to just kind of come up with a root cause here. And this is happening at a 10,000x scale across our network at all points in time. So we have to come up with a strategy as to how we deal with this. The first step is to become topology aware in our correlations. So our correlation engine will intake all of these events. It will compare it against the topology, which we have configured within the correlation engine, essentially establishing a relationship between different layers of our network and how they're related. And that initially gives us a first pass where at least we have all of the events ranked from a topological perspective. The second thing that needs to happen, because we have multiple root cause events happening on the same topology at the same time, is we need to then also become event aware. And so we'll do a second pass of correlation, at which point it will categorize certain events, and you can see certain events marked in like the lighter colors, as being essentially part of a root cause. In this case, we have a fabric switch failure. It's causing both upstream and downstream events. Now, the rate at which this is happening in the meta network is at a rate of something like 250 to 1. So for every 250 detections, we're getting one root cause. This allows us to maintain a very, very high fidelity and granularity on our detections, while also minimizing and reducing the noise that's going downstream in our pipeline to our repair processes. Now, occasionally, we need a slightly more advanced triage and root cause. And support engineers and our vendors occasionally have to do triage on the fly for maybe a problem that we couldn't automatically triage. And so to this end, we love on-box agents. So we've built another on-box agent, which essentially captures a snapshot of detailed events at the time of the incident. So in this case, it's taking snapshots of routing tables and vendor-specific tech support commands and other commands that our forwarding stack engineers might need to see. It does these, it aggregates them, it uploads them, and then it attaches it to any of the support tickets that our support teams or engineers might be using to debug or triage this problem in the past. Additionally, even if the device doesn't need to be manually triaged, we're stashing these centrally so they can be analyzed in the future against our triage results that we've had in the past. The other thing that the other benefit that we found from this is that we automatically integrate this with our vendor management platform. So we speed up the RMA process. Our vendors are no longer going back and forth with our support teams. They have direct access to the triage details of a problem that we've identified as an RMA. And this has significantly helped us reduce the overall time to repair for these types of events. And then finally, we need to talk about robust SLOs and mean time to repair. So we were talking about rapid repair as being, it's the final thing in this step, and oftentimes this is a manual human process. And what we found is that no matter how good we are at triage and now how good we are at detections, it's really a ruthless focus on mean time to repair that enables us to continue to operate at the level that we're operating at. We use MTTR not as a theoretical goal, but as an operational metric that we look at on a daily basis. And we use this to drive improvements to our correlation, to our triage accuracy, to our auto repair actions, and streamlining RMA. Now, we can break this down into smaller components, and we can analyze these things in smaller components to make progress. But ultimately, the single focus on a top-line MTTR is what has enabled us to drive the improvements in the repair process. So now, as we move forward, I'm going to transition back to Jose, and he's going to cover the results and observations from our initiatives.
Good job. So thank you, Rob. It is interesting to understand that as a result of all these efforts, we have been able to achieve improvements and, most importantly, consistency in every step of this pipeline, where we're talking about detection, mitigation, triage, or repair. One of the interesting things about this is that having this data and having this analysis that Rob was just describing have given us the ability to understand patterns that before were either anecdotal or we were simply not aware. And this is manifested in the fact that one of these is that not all failures are equal. And this is really interesting because most of us will have some anecdotal view on this, but actually having that hard data to see that there are a number of failures that have an outsized level of impact has really provided clarity for us and for our teams on where to invest next, where to put our energy, time, and effort to make sure that this translates to something that is meaningful for the AI training, is meaningful for our developers. So this has been really, really great. The second one is that systemic issues really matter. And this has been the improvement on refinement of how we handle things such as repeat offenders or what I lovingly call slow burn type of issues. And this has been critical because what we saw was that these issues were consuming resources on the data center. These are the folks that actually need to go do the repairs. We were essentially removing capacity from the network that didn't need to be removed, or we were removing it way too much instead of actually fixing the issue. And ultimately, a lot of these cases just ended up in no fault found type of repairs. We saw this mostly around optics and certain temperature anomalies. The third, which Rob talked about as well, is that time to repair is critical. By having this discipline and by ensuring that we can keep the network within that reliability envelope as redundant as possible, as available as possible, we have seen how what were before were essentially major issues have essentially been reduced to minor inconveniences that can be handled mostly by automation or with less severity than before. So ensuring that we have these investments has been critical for customer experience and has been critical to keep the network within the envelope and within the expectations of our customers. So if we come back to the question that Rob posed before of can we predict and mitigate failures before they impact jobs, our answer today is that yes, we can. If we think about the future, there are many things that we are exploring, but the most interesting ones or the most relevant or the ones I care about most are these three. First one is active monitoring. Active monitoring for us has always been the gift that keeps on giving. And in the case of AI, this has been 10x. We have seen how active monitoring has been invaluable, and we want to continue exploring use cases like at the application level. The example that we have here is bit flips. This typically is very difficult to triage. It involves mixing different worlds from the host, from the network, from the ASIC, depending on what it is. So we see opportunities there to continue developing this with active monitoring. The second one is improving the accuracy of triage when we have cases that go for a really long time. An example of this is when we do certain types of hardware replacement, where essentially we have signal and we believe this is this particular some component within the system. We send this to be replaced. It gets replaced, happy days. This then is shipped to a lab where either ourselves or perhaps a vendor has to do failure analysis. Having that information and feeding it back into the system about how accurate our analysis was is really crucial to be more efficient, and it's really crucial to be able to repair capacity in less time, in less touches. A technician has only to do one option, has only to do one action in order to repair the device instead of having to go multiple times. And the third one is essentially continuing to expand network SLI to be able to address more scopes and go deeper into latency. And we see this because future topologies have an even higher reliability bar, and we want to ensure that our approach remains to be viable before we actually see those technologies in production. So some takeaways from us. I think the first one is GPU workloads have drastically increased that reliability and performance bar. This has been a forcing function for us to revisit how we did a number of things for many years and how to take these things to the next level. And on the second takeaway, we have been able to hit most of those targets and in some cases even exceed them. And we give credit to our own in-house solutions because they have provided the flexibility to experiment, and they have provided the flexibility for us to do things that are across many different domains that are somewhat disjointed at the moment. And the last one, which I think is the most interesting one, is that technology, techniques, and demands that we talked about today are essentially, the solutions that we talked about today are essentially about what we saw. But if we look at the future, if we look at the new designs, if we look at what's coming, there is going to be an even deeper emphasis on reliability, on handling these failures, and in essentially being able to be more predictive than reactive. And for this, we continuously do experimentation and investments to ensure that we are ahead of the game. With that, thank you very much. Happy to go to Q&A.